Does data. Tonight we are continuing our modeling of For Well Thou Can, or For Well Thou Knowst. We are doing font recognition of Shakespearean text in 5 different fonts that we have. So last week, if you might recall, I was just looking, how am I going to read in this data set? The data set, if you don't remember, if I remember, nope, tab new, do font, of course. Let me publish this to Reddit. I gotta remember to do that. Hello, Reddit. If you want to downvote me, now's a good time to do that. Just get it right out of the way. So last time I walked through making the stupid data set. Just a bunch of images of fonts. But I'm taking images of Shakespearean text, of course. Or I'm using Shakespearean text as the text that I'm writing out in these 5 fonts. So last time we built a data set. We got our labels. And that almost worked because auto indent, always good to have. There we go. This takes, less than a minute to read in. Tasty. Okay. Data, yes, I've got 500,000 or so. 500,000, yeah, I've got like 100,000 lines of text, because that's a lot of Shakespeare. And we're looking at the first, I think, 16 characters I said of each one. We can see right here. Yeah, 16 characters. And that's because data of like 2,000 is For Well Thou Knowst. I believe that might be true. Let's just remind ourselves what it looked like. Tonight's goal, we want to actually do some modeling. I'm just going to try to start with like the brain dead simplest model of let's just build logistic regression, because that's easy. That proves that we can actually build a model that does something probably not very good, but that's okay. But I want to import matplotlib as .pyplot as plot first. Plot.ion. This is really no longer going to be data in. It's going to be some simple model, which is fine. Let's do that. And plot.pcolorMesh of data 2000. What does that look like? Is this going to be upside down? Nope. As promised, here is the tagline of this. Maybe that should be the logo. I made up a stupid logo for the previous video, but maybe it should be this. You like crazy colors? You don't like crazy colors? Well, then we can just do plot.cmap.gray. We can do plot.cm. Then if you don't like crazy colors, we can do this. And again, much harder to read fonts when they're spread out like that. Okay. But that's not what we're here to do. We are here to build a simple model is the goal, because we also have labels. My labels are already in one hot format. They already are. I saved them like that because I was good. So I need to build a simple Keras model. And the question is, do I remember how to do that? And the answer is probably not. I'm going to put this import Keras down here just so I remind myself that. Build Keras model. Inevitably, I'm going to want to look at Keras.io to remind myself how to do this. Even though it wasn't that long ago that I built this model. Actually, I can probably tab new proj. Do I have a Keras thing? I do. Keras tutorial. There we go. Alright, so I got all this stuff. That's right. Gotta get some of that. So things from Keras that I might need. I'm not going to need numpy utils. We might get to convolutions. We'll see. These images, however, are quite large, relatively speaking. They're 128 pixels by, I think, 16 pixels. Sorry, they're not huge. Let's be honest. They're not huge. But it's not trivial compared to like the MNIST 28 by 28. It's not something to just laugh at. Alright, let me steal some old code of mine. And let's not even build a neural net yet. I just want 5 classes, input shape equals 128 times 16. Comma, whatever that is. Okay. So we're building a sequential model. We're just going to start with logistic regression. So there's 5 scores you're computing. That's what the 5 there is. And our input shape is 128 times 16, which is how big the data is. 2048. Oh, nice. I should have known that. Because data 0.shape I can ask for is that, yes. In activation softmax, which is just saying logistic regression. And let me run that. What kind of gradient descent are we doing? We're going to compile. That doesn't take long anymore because it doesn't actually compile until you do the fit. Which is kind of a drag. Okay. See if I can just chunk data in here and see what happens. Labels. Oh, I need test and validation data set. Right. Right. Can I have Keras do that for me? Validation split. There we go. Woo. I might regret this later. That I don't split my data out on its own. Yes. Let's say, I don't know, 20%? Let's try 20%. And that's honestly because I don't want to be modeling on that much data. That's the real reason. We compiled. Let's see how this goes. It's got to compile the first time, so it's going to take a little while. I'm not going to have this many weights. So again, just a simple logistic regression model just to get things going. And it's taking a long time to compile, of course, which is why I wish it's still compiled on the compile line here. That would be great. I guess I'll take this opportunity to talk about this GitHub page I've set up for this project. So at github.com/dvbuntu, which is me, /forwillthou KN only, I've got a GitHub repository of the code that I have here. So it briefly explains what the heck this is, and it's Tuesdays at 6, of course, that you can watch me. And there's more videos on YouTube. The data set that I've pre-made is on Google Drive. It's about a gigabyte. If you want to make your own, you can do that. You can use like any set of text that you really want. And this is where we are so far. So we already created this data set, font data, and we read in the data. And tonight, we want to basically get this far. Like this is this video right here, right now, which I'm not going to go visit. This is still waiting. That's frustrating. Am I using up all of my memory? I am, aren't I? Oh, okay, didn't like that. Bad input. Oh, no. I see. Right. All right. I need to reshape the data. Alright, so can I Keras reshape? I know you can in like Theano and TensorFlow. Reshape layer. Core layers, flatten, reshape. This might take a little longer to compute, but I'm gonna not destroy my memory on my machine, so that's a plus. Only 16%. I could afford a double, right? Yeah, you know what? I can. I can do that. Let's make a flat data set. Data.reshape. Does that work again? Just whatever the new shape is. Okay. And I just want it to be -1. I say whatever it's supposed to be, 128 times 16. Yeah, that's what we want. And that should totally wreck my memory situation, but it doesn't. I wonder if it's pretty smart about storing that. It knows, oh yeah, that's just, I don't know how to do that. Now this shouldn't take as frigging long. Yes, there we go. Alright, this is actually not bad. So it's going to take me, you know, roughly 10 to 15 seconds to do 10 epochs, so that's not bad at all. And our accuracy is actually holding steady at 60%. Oh! No, it's 10 to 15 seconds per epoch. Ooh, that's going to be trouble. This could take a while. Perhaps I should have computed this on a much smaller validation accuracy. 0. That's interesting. I wonder why that is. So this accuracy suggests that it's getting 3 classes correct all the time. And the other 2 classes, I'm just betting, willing to bet, that it's always stuffing one of those into yet another class. Well, I wonder... Yeah. This validation accuracy 0 is troubling, though. Very troubling, very troubling. This is climbing. The accuracy here. The loss, of course, is getting better. The validation loss, not changing one bit. That is disconcerting. I'm not a fan of that. I say validation loss not changing. Loss not changing. Like, if it was getting worse, I could get behind that. I could say, alright, well, you know, things happen. Machine learning, validation error, less than training error. Yeah, that can happen. High validation accuracy. So this is weird. Yeah, but our training accuracy is doing, again, not great. We're going to look at the confusion matrix after this. And the weights and all the good stuff. All that good stuff. So I'm going to need to reshape these weights, which of course I'm going to steal some old stuff to do, because that's how I work. There we go. I apologize if I'm like sweating profusely as it's extraordinarily hot. My air conditioning did get fixed. Why validation accuracy 0? That's strange. If someone wants to yell at me and tell me I'm doing something stupid, now is the perfect time to do that. Always a good time to tell me I'm doing something stupid. And I see I've already been downvoted on Reddit. Thank you, Reddit. I appreciate that. Always like to get those downvotes. Oh, this is to do a 2-dimensional plot. Well, 1 and... no. 5 and 1. There we go. That's Y. Where's SX? Let's see if I can get away with this. Reshape 16 128. Alright, let's get some model. Let's get some of that. We have weights. They might just be random. These are all basically 0, I think. Yeah, relative to these weights. Oh, did I not scale my data? That shouldn't matter. Data 0. Hang on, numpy.max take 0. No, that's fine. That's weird that it's 254 rather than 255. So, like, you could scale these 0 to 1, but who cares? That doesn't really matter. Let's see if I can get away with this. Too many indices for array. Yeah, I thought that might be a problem. Plot.subplots. How does that work? No, that's... Because that gives me 5 in a column, which I guess is fine. I don't mind 5 in a column. But I don't actually have this. Right. It's a problem with range, really. Too many indices for array. Really? Oh, because it's talking about YY. Equals 0. I'm going to leave this line here, but I'm going to comment it out. Too many indices for array. Ooh, wait. W1 doesn't have that many? (2048) rows, 5 columns. Subplot axes, positioned by whatever. Yeah, I just want to plot that. What did I do this before? Yeah, I didn't deal with this before. X, Y, Y. Those are all 0. X, Y. That's 0 then. So it should be W1 of everything comma 0. Right? Which is the thing. And reshape. 16. Oh, it's not going to like that, is it? No, that's fine. It is not like con, I guess? Con.shape? 5 comma. Alright, let me just make this 2. Even though I don't have more things, I don't want to fight with it. Oh, freaking, come on. Therein lies the problem. 1, 5. Let's try that. Nope. Nope. Con.shape. 2, 5. You'd think I'd know how to do this by now. You'd think. You would think. Index 5 is out of bounds for axis 1 with size 5. There shouldn't be an index 5 there, Chief. Don't know what your glitch is. Oh boy. This should not be that much rocket science. No, it should not. Alright, I'm just gonna friggin' matplotlib subplot pcolor. Let's have a look-see at this. Yeah, well, that's cute. Yeah, there they make each individual subplot, which I don't really want to do. And there's 2 by 2, and this is in the first position, the second position, the third position, the fourth position. Yeah, not really what I want. Oh, actually, that ain't bad. What is F in this case? F is the overall figure. Con is a list of subplots. So I don't have to make the figure first, I guess. Oh, but if I want to share X and share Y, I probably do, don't I? Yep, yeah, I do. con dot shape. Screw it with this one, and I'll say con equals con dot reshape. SSXY. Yeah, no, that's cute. That's great. Con dot shape. There we go. There we go. There we go. Range 1. That should give me a 0. Yeah. Should all be hunky-dory. Index 1 is out of bounds for axis 1. See, I don't think that's actually true. XX. YY. How is YY 1, Chief? Because I have the wrong freaking number in there. It's even highlighted for me, you know? You'd think I would pick up on that. So I'm always yelling at people when they stream and are doing things wrong. This is about what I expected, yes. So you've got 3 classes where you've got some scores of some kind or another. This one is big score. You know what? Let's use cmap equals plot.cm.gray. So gray R. So black things will be large numbers, big weights. White things will be negative. Yeah. So this is positive. You know what? No, I like it the way before. I apologize for all the plot.cm. What are my options here? .magma, inferno, greens. Definitely not greens. Definitely never go with greens. It's impossible to tell greens apart. I'm not even colorblind. It's a bad, bad idea. Hot. Let's do that. There we go. That's a little better. Alright, so these 2 fonts have they're interested in things, lines up here, saying, oh, if this font reaches up here, this is important. This one is like the opposite. If you reach up to this point, that's not important. This 3rd font says, hey, things in this region are important, whereas things over here and over there are not. This is perplexing to me. I can't fathom why a font would care where in the words something is important or not. And that it's very important that things are here and not here. Oh, maybe this. So I've centered all the phrases. This font number 2 here, 012, probably has more things centered, and it's just a smaller width font, and so it doesn't actually use things on the left and right here. Whereas these guys definitely do. This one gets high, this one is long, and fonts 4 and 5 are still pretty random. What's interesting, but fonts 3 and 4, this one has a lot of dark squares, which I believe are as negative as possible. This one, not so many. That's just weird. But we should get the confusion matrix too. Did I do that in here? Conf maybe? No. Alright. So I guess we gotta make it ourselves. We're gonna need model.predict, I think. Model.predict. Oh boy, oh boy, oh boy. And we'll just have to do it on a whole data set, and that's fine. Let's see if Keras has it built in. If it does, that'll save us some extra. sklearn does. Yeah, you know, let's just use sklearns. They know how to do it. They do it right. It'll save me some headache. Let's just import sklearn. Preds equals model.predict of data flat, right? That's how we use that. Yeah. Y true, Y pred, and labels. Oh, these are the actual labels, right? So I'll need to convert my convert my labels from one hot encoding, which is kind of a drag, but that's okay. Dummy.argmax. Dummy.argmax. And it's going to be like axis equals 1 or something. X equals 1. Let's try that. Check to make sure I'm not soaking up all my memory. We're getting there. Definitely getting there. What's left at Preds? Length of Preds. This should be a big long list of all those. Yep. And labs is just going to be the same thing. But instead of on our predictions, it's on our actual labels. One hot encoded. Labels. Yeah, there we go. Okay. So I'm going to say conf equals sklearn dot. Sklearn dot. Is there just a confusion? Ah, come on. Sklearn dot metrics. Apparently you can't. It's something I hate about sklearn. You can't just import. I can't just import sklearn and then call things from it. I have to import specifically whatever .metrics say. If I say import sklearn.metrics as metrics, it's one of those things that irritates me. If I import the top level module, I would like to be able to access everything in the module. Yes, my namespace will get very long, but that's okay. And it's true, then predictions. Labs, Preds. And labels? Optional, yeah. It should be able to figure that out. And I can look at the confusion matrix. Yeah, and so this is pretty much correct. This is pretty much correct. This is pretty much correct. And then you'll notice it's never predicting class 4, 3, or 4. It's for class 3, it's usually predicting class 1. And for class 4, it's splitting it between 1 and 2, which is interesting. Yeah, that is interesting. Let's tell you what. Let's take a look-see at our data again to try to assess why that is. Here we go. Length of data. How big is our data? How many do we have here? Okay. Num images, not num images, num phrases. Length of data divided by 5. Now I'm going to do a subplot again. A subplot with one set here. I just got 5 and 1. Yeah, and that's fine. That's all I need. We're going to say 4, I in range 5. Con of I equals, is that right? No, dot p color mesh. Okay, okay. There we go. 2000 plus I times num phrases. So we're going to plot all of that are our choice phrase for well thou knowest in all the fonts. Yeah. And so you see, of course, font 2 here, very squished. Font 0, it reaches higher than some of the others. But like for font 4, it should really be able to figure this out. There's some good indicators on the left and the right here. And for font or excuse me, font 3. This is font 3. And for font 4, this is narrow, but not as narrow as this one. Good gravy, this one is a huge pain. I don't know, but you basically can't even read that. And again, maybe if it's size 12 there. No, that's still 12's really smaller than that. Alright, so I want to get this so it can actually give me something for this. It may just be that it's stuck in a bad place in the model. So we're going to redo the model. Just for giggles here. I'm going to cut the number of epochs down to 1, actually. Because I don't think that's going to... Like, it was getting about 60% accuracy. Why validation accuracy was 0? Yeah, so look, now it's getting... It's 40%. I think I'm just going to have to split the data into something reasonable. And take the same phrases out of each one. Oh yeah, but check this out. Validation accuracy, 0.99 now. You know why? I don't know why. It's a mystery to me. Let's get some weights. Let's take a look. Like, yeah. So now we're modeling these last two. But not these at all. And you know what's interesting? And so it's doing the same thing. This is a wider font, of course. This is a narrower font. So it says, hey, if your things are in here, that's a very good score for this font. If it's out here, that's score against this font. And the opposite is true here. But why? Oh, is my validation split? Oh, I'm suspicious now. Validation split. Fraction of data to use held out validation data. I gotta close some of this stuff. Validation split. Yeah, does validation randomly choose validation sample? This is a good question, because I don't think it's... The model's up high. Selects the first 90%. It might just select a random chunk, contiguous chunk. Picked as the last 10%. Alright. So I need to split the data myself, then. Okay. Here's what we're going to do. I'm going to numpy.random.seed 0. And this is how we're going to make sure we split the data the same every time. And where do I want to put that? After I read in the data, of course. And now I want to split data into training/validation. And you know what? I'm going to split it 50-50. Just because I don't want to have to read in that stuff again. So, and I want the same phrases in each. Equals data, let's see. Test flat. Labels flat. Oh, no. Test labs. There we go. So let's do that. So we need to think about this right. Here we go. We'll do it after here. This is, let me add a comment for myself. Plot images of a phrase in 5 fonts. Let's put that into training validation. There we go. Okay. So I want to generate a random permutation of all the possible phrases here, right? And then I just want to take the top half and the bottom half of each and form my data that way. So I want numpy.random.sample. Sample, is that it? Returns random floats. I've said no. Dot pop? No. Where is that? I thought I could have sworn it was sample. Random floats in half open interval. That's not right at all. There's a way to get a random from a population. Choice, maybe? Generates a random sample from a given 1D array. If A is... Right, okay. So I want my train indices to be numpy.random. Let's seed it right here. Just so I know. That choice of... Son of a gun. Alright, fine. Num phrases... Random.choice. Make sure I know how this works. Whatever the thing I'm doing it on. So I want a list of numbers, because these are the indices. And how many? Size equals num phrases divided by 2. And then that will mean that the test indices are everything else. Oh, man. So I'm going to want a stupid way to do this of just saying I for I in numpy.arange num phrases if I not in train index. Stupid way to do it, but that's fine. Okay, so now we're going to have some indices to select our training and testing data sets. This big old, shoot, I should. I can't use, I have 500,000, so I have to use an integer of like size 64, which is unfortunate. Or no, 32. Dtype equals uint 30 numpy dot uint 32, right? Because that goes up to like 1 billion. Whereas 16 would only go up to like 65,000. Dtype is unexpected? Oh, I should use it on the A range, right. Of course. Try that. One more time. Much quicker, much better. That's not as quick because I have to do this stupid list comprehension, but it works. Let me TQDM that so I don't go crazy. There we go, okay. And so you should see that length of train index and length of test index are not almost the same. That's interesting. Num phrases. Plus. That's interesting. Alright, so I've done something wrong already. But so it's not, I'm reusing something somewhere. I don't know why. Randomly seeded again. Num phrases divided by 2. 53105 times 2. Yeah. I for I in whatever, if I is not in train index. Yeah. Of which there ought to be damn well. That's super weird. Super duper weird. Yeah. Hang on, let's see here. Playing test index. Lies and slander. Set of test index dot intersect set of train index. What went wrong here? Oh, set dot intersection. Excuse me. Nouns instead of verbs. It claims those are the empty set. And yet I deny that that could be the case. I suspect... That makes no sense. No, this is impossible. I realize we're getting distracted by seemingly unimportant things. If I take this and subtract out all the things I have, you'd think I'd get that, right? You'd think. You would think. I wonder if it's a... this could be... I might be... It's some type of data type issue that I've got like 1.0 somewhere stored as like a Python float, essentially. But it's not... But in the array, of course, it's stored as like a numpy integer. And it's not realizing those are the same things. So actually, there's a better way to do this. I think. I'm pretty sure there's a better way to do this. Let's nuke this. I don't like that anyway. Let's just say set numpy.arange. Let's grab this. All the things there. Numpy.arange of this thing, sure. Dot disjoint. Difference. Ooh, difference. Does that tell me what I want? Return the difference of two or more sets as a new set. I.e. all the elements that are in this set, but not the others. Perfect. Dot difference set of train index. That should tell me what I want. And of course I want an array of this. Numpy.array dtype equals numpy.uint32. Int argument must be a string, a byte's not a set. Alright, of course that means I don't know which set. Which one of these things is the problem? What if I just work with this first? Alright, there's a thing there. Is that the right length? What's going on? Why? Length of test index. Sorry, length of train index. I must be like missing something really obvious. Length of set of this? Why are there repeated values? Ah, come on. Numpy.random.choice, you're killing me. I thought you gave me a unique. I could have sworn replace equals true. Curse you. Place equals false. I want everyone to be unique. And actually, let me just do the stupid thing. Yeah, let me just go back several to when I was doing this the stupid way. And just add in. Replace equals plus. Alright, so this takes 10 minutes to do, but whatever, that's fine. That is, as they say, totally fine. That's data flat. Let's make train flat equals data flat of train index. This is test flat. Test index. Labels. Train test. What do I call it? Test labs? Labs test? Test labs. And these Train labs, yes. Okay. Just so I don't go crazy, let's do that. Length of data flat. Let's, yes, length of train flat. Which is, oh, you know what? My bad, my bad. Right, so that's just the phrases that I'm pulling out. But I want to pull out the same phrases from every guy. Right, so P, so we're going to call these for phrase. And then the true train index, of course. I didn't really need to redo that, that's fine. I want numpy.concatenate, right? Concatenate. That preserves input masks. Yada, yada, yada. Sequence of arrays. Yes, perfect. Because I will want ptrain idx times I? No. Plus num phrases. Times I. For I in range 5. Somewhere I've got like a num fonts, don't I? Num font. Label list equals list. I thought I did. Well, whatever. That's fine, that's fine. Then I play the same game with the testing. P test. So I'm just making sure to grab all the same phrases in all the fonts. So like the train index should be about half the whole data set, 250,000. Like the test index should be about half the whole data set. 5 more, because it was 1 more phrase and there's 5 fonts. Okay, now we're cooking. So now I've got a particular data set. So I can build my model. Do that. And we're not going to fit that. We're going to fit with train flat and train labs. There we go. I can afford to go up to 2 epochs now, of course. See how that goes. Yeah, so it takes less time to train because I'm using less data to train, of course. So that's on all the data. Let's use test right here. Test labs. Yeah, there we go. So yeah, we're getting this like 39% because I bet we're getting 2. It's like falling into one of 2 sets of things. It either does the first set correctly or the last set correctly. Sorry, the first 3 fonts or the last 2. Oh, no, it did it differently. Here it's just looking at the first one versus the last one, which is interesting. And I imagine we're going to see that reflected in the confusion matrix too then. And again, we're just building the simplest model we can. What's conf look like? Yeah. The first one, and the last one. And the other 3 classes. This class, it's mostly class 0, some of this. This middle class is all class 5. Or class 4, excuse me. And this one, it's all mostly here. So if I just train for a much longer time, say, just hypothetically, if we were to do 20 epochs, forever, I know. This will be 20, so this will take like 2 minutes to train. See if it gets anywhere. But the validation accuracy should at least be fair now. Yeah, it gets a chance to look at all of the model, all of the phrases. So that's at least a fair assessment, which seems to be dominated just by the first and last. You see, at least these numbers are vaguely the same. Validation accuracy and the actual accuracy. There we go. The loss is slowly improving, right? Is getting worse. That's interesting. There's an improvement, okay. 6856, 6896. Yeah, you would have thought that would have improved more. Alright, so that was just the goal. To be able to get a basic model working. And like, it's not great, it's not a good model, not by any stretch of the imagination. But we're reading in data, we're building some kind of model. Again, in this case, it's just a simple logistic regression. We've commented out these neural network lines, because I guarantee that's gonna take a lot longer to compute. Right now, we've got 128 times 16, so 2048 times 5. So basically, like 10,000 parameters plus 5. 10,000 parameters to estimate. If you have a neural net that has more than 5 nodes in that first layer, well, then you're going to have a whole lot more. So say you had 10 nodes in the first layer, now you've got 20,000 things to compute. Plus, you know, like 20 times 5. Almost nothing. It's this first layer with all these pixels that's really determining how many things we need. And if we had more layers in the middle, say you had like, oh, we'll do 32 nodes in the first layer, and then 32 more nodes, well, that's 32 times 32. It's even more things, more parameters. It adds up over time. This accuracy not really moving a whole lot. Neither is this loss. Is it even 6878, 6856, 6856, 6856, 6856? It seems stuck. Not really going anywhere. 6856. Show me 685. Yeah, it's not going anywhere. Let me kill that. It is climbed as much as it's going to climb right now, I think. Why is it going on with my mouse? Yeah, it's very clearly saying, alright, if I see some things out here, or things up here, it's this font. If I see things in the middle, but not out there, it's this font. Anything else? I have no idea. These are totally random, I bet. And this is biased towards like one of the other classes. I think that's what the confusion matrix showed us. I tell you what, let's be bold. Let's say we have a neural network with, 16. I think I can get away with this. We're going to find out here real quick. Let's try to build a simple neural net. See how long it's going to take. We're not going to train for 20 epochs. No way that's going to happen. Because we've got, yeah, like 3 times as many things to deal with here. Let's try this. It's got to compile the first time. Question from the audience. Is this running off Theano or TensorFlow? I'm running off Theano because Theano recognizes my GPU and TensorFlow doesn't. So for me, it's faster to use Theano. But you can use whatever you like, whatever works best for you. That is training faster than I would have expected. Oh my goodness. And the accuracy is good gravy. What? 98%. That is much, much higher than I would have expected. And that's validation accuracy. Alright, so this problem might be done sooner than I would have thought. That's incredible. Oh, come on. Oh, alright. W2, B2. W2, B2. There we go. Woo! Alright, I no longer have 5, now I've got 16. Right? Yeah. Let's go 8 by 2, shall we? 2 by 8. Let's try that. Which GPU am I using? I don't actually remember which GPU I'm using because I'm a terrible person. NVIDIA SMI. I am using a GeForce GT 620. It's like a gamer grade GPU from like 4 years ago. So it's only got 2 gigs of RAM. It doesn't run a new cuDNN. But it is an NVIDIA card. What was I doing here? I was saying this was silly. I'm just going to do 16 by watt. I wanted to see what these weights all look like. Jeez, oh man. So, I'm getting some interesting stripes that it's computing in a lot of these. And this one, some are just like, this is super hot. This is super cold. Interesting. We can also just look at W2, which W2 is just those 16 into 5 classes. Let me do gray R. Equals plot.cm.gray. Yeah, that's fine. You know what? I really don't like that. Hot. There we go. Oh, that's a little better. And I'm not seeing anything super. These are the 16 different neurons, how they activate different classes. Some, like this neuron, basically hits this class a ton. Someone asked, what is the system that you use? You're going to have to be a little more specific in what you mean by that. I'm running Arch Linux, and I'm using Keras with with Theano as a backend. And it's all in Python, on my programming end. Yeah, so really I see just a couple key neurons that are like hot on a couple things. So this first neuron is hot on this first model. And it looks like the confusion matrix, which is going to be super good. Let's do that. It takes a little time to compute now, of course. Conf. You know what? Let's do plot.pcolor conf. That's, hang on. Plot.mateshow conf. There we go. It's the things get inverted when you plot, and yeah, things to keep an eye on. Oh, so for all my pcolor plotting with this other stuff, I might be doing that a little goofy. And flip-flop your top and bottom. So this is almost super solid. There's a couple instances of this that are off, of course. So what is that telling me? That's telling me that Class 1 and Class 3 are the trouble classes. They are harder to distinguish each other. Which, if you recall, this is probably how we'll finish off this video. Those classes are the 2 narrow classes. Those fonts are the 2 narrow fonts. Did that run? Are we running? Shouldn't take that long. There we go. There we go. Yes, font 2 and font 4, excuse me. Those are the 2 narrow classes. So it is not at all surprising that it tends to get those 2 things confused. And imagine, it's just certain letters tend to be narrow in one, aren't as narrow in the other. Like this one, L is, what is this, like an all caps font? I'm not even sure. But in whatever this font is, the L's perhaps are very, very wide, and maybe they're not here. So when this one has lots of L's, it tends to be a little wider. There's other things that could be interesting here. I did not expect that model to get like 97%, but I'm sure it's doing almost a lot. Totally, what's the length? What's the length of interesting things in this area? So maybe I want to revise the data set. Maybe I want to stretch them all out to a common length. Maybe something like that. Maybe I want to cram as much phrase as I can into whatever this box is. That might be an option. Something like that. And then so that would identify different fonts. Because basically, yeah, now we're just using the size. They might all be about the same size tall, some more so than others, like the F here, super short, or the L is very tall. But in the first font, the F and the L is pretty much the same height. And this is like another, almost all, everything's the same height in this font. Whereas in this one, we have actual differences. F is tall, L is tall, lowercase e, not so tall. Alright, so building a simple, stupid neural network. Amazingly did a pretty great job, 97%. I challenge you to take the same data, build a much better model. It's going to be not hard to beat, I'm sure. I have to imagine the neural net just let us climb out of that that local maxima that the logistic regression was getting stuck in. But other than that, I think that's all I got for tonight. We have a simple model. We've got even a simple neural network. So thank you all for watching. Keep the questions coming. Hit me up on Twitter. Hit me up on YouTube comments. Downvote me on Reddit if that's what you want to do. So make sure you keep looking at data. Stay safe in the data mines.